Good morning. I am Dr. Srinivasa, working as an assistant professor of physics in IDSG Government College, Chikmagalur. In this video, I am going to explain some concept of natural radioactivity, which is a chapter for 3rd BSc Physics students in a paper Nuclear and Particle Physics, subject code SSF 611, and this is the session number 4. What is natural radioactivity? Radioactivity is the spontaneous disintegration or decay of the nuclei of certain heavy atoms with the emission of one or more types of radiation, or the phenomenon of spontaneous emission or disintegration of radiations from a heavy elements of atomic number greater than 82 occurring in nature is called natural radioactivity. Natural radioactivity is the phenomenon of spontaneous emission or disintegration of radiations from a naturally occurring heavy elements. Nuclei, why the radioactivity exists or occurs or takes place. Nuclei of certain isotopes are unstable. You know that nuclei of certain isotopes are unstable. That is, they contain excess energy. In order to become more stable, they need to emit energy. So, to acquire stable configuration from unstable configuration, they emit excess energy in the form of radiations. This process is known as radioactive decay. The radioactivity phenomena was first discovered in 1896 by Becquerel. Substances which exhibit radioactivity are called radioactive substances. The substances which exhibit radioactivity are called radioactive substances. The rays which are emitted by radioactive substance are called radioactive rays or Becquerel rays or disintegration rays. The rays which are emitted by a radioactive substance are called radioactive rays. They are also called Becquerel rays. There are 3 important types of radiation which are emitted by the nucleus, namely alpha radiation, beta radiation and gamma radiation. 3 types of the radiations which are emitted from the radioactive substance are alpha, beta and gamma radiations. As the heavier atoms become more unstable because they consist of large number of protons and neutrons, they become unstable. To attain stable configuration, they emit the energy in the form of particles and also photons. It is called radioactivity, and the substances which exhibit these phenomena are called radioactive substances. So, for example, this is the radioactive substance. This radioactive substance emit 3 types of radiations: alpha rays, beta rays and gamma rays. In beta, there are 2 types. Beta particle, nothing but electron, negative decay, and also there is a positron decay. So, the emission of the positron from the radioactive nucleus. You all know that alpha particles are nothing but helium nuclei having positive charge. This beta particle is nothing but electron, and this is the positron, and this is the gamma ray photon also emitted after the emission of alpha and beta particles. So alpha particles, beta particles, in that electrons and also positrons and gamma rays are emitted from the radioactive substance. The radioactivity is not affected by external conditions such as physical change, chemical change, pressure, temperature, electric field and magnetic field. I mean, the radioactivity does not affected by all these factors. Applying all these parameters to the radioactivity will not change. So, the radioactivity is not affected by external conditions such as physical change, chemical change, and also by applying pressure, and also temperature and electric field, magnetic field, etc. General properties of the radioactive rays. The radioactive rays affect photographic plates. All radioactive rays, alpha, beta and gamma rays affect photographic plate. They can ionize the gases when they pass through them. They can also penetrate through matter, and also they exhibit fluorescence and also phosphorescence, and also the ionizing power of alpha rays is greater than beta and also gamma, but the penetrating power of alpha rays is very much less than beta and gamma rays. Ionizing power of alpha rays is greater than beta and gamma, and the penetrating power of alpha rays is very much less than beta and gamma rays. Radioactive disintegration. So what is radioactive disintegration or decay? We know that heavy elements like uranium, thorium, polonium, radium, etc. spontaneously disintegrate, giving out alpha, beta and gamma radiations is called radioactive disintegrations or radioactive decay. That means the number of nuclei in that substance goes on decreases when they are emitting alpha, beta and gamma radiations. When an atom of an element emits either alpha or beta particle followed by gamma rays, the atom becomes a new atom of a new element. When an atom of an element emits either alpha or beta particle followed by gamma rays, the atom becomes an atom of new element. The earlier element is called parent element, and the new element or product element is called daughter element. The daughters may also be radioactive and disintegrate into an atom of new element. This process continues until a stable end product is obtained. The series of elements produced due to series of disintegration is called radioactive series. In a radioactive disintegration process, a series of new elements are formed. These series of new elements formed are called radioactive series. Radioactive series. There are mainly three types of naturally occurring radioactive series, and fourth one is the artificial series. So the three naturally occurring radioactive series are: first one, uranium series, in which uranium-238 is the parent member and the end product is the lead-206. And the second one is actinium series, in which uranium-235 is the parent member and the end product is lead-207. And the third one is thorium series, in which thorium-232 is the starting element or parent member and end product is lead-208. The fourth artificially produced series is neptunium series, in which 93 neptunium-237 is the parent member or starting element and the end product is bismuth-209. Here the end product is different. In all these cases, lead is the stable isotope of lead. 206, 207, 208 are the end products in the naturally occurring radioactive series. But in the artificially produced series, the bismuth-209 is the end product and the neptunium-237 is the starting or parent member. So Three natural occurring series are uranium series, actinium series, thorium series, and the fourth artificially produced series is neptunium series. So these three are naturally occurring radioactive series, and this one is the artificially produced series. Law of radioactive decay. Before going to understand the radioactivity phenomena, we have to know some terms. The first one is law of radioactive decay or disintegration. It states that number of nuclei decaying per second, that is also called activity, is directly proportional to the number of nuclei present in the sample at that instant of time. Rate of radioactive decay is directly proportional to number of nuclei present in the sample at that instant of time. Is called law of radioactive decay. Let n be the number of atoms present in a particular radioactive element at a given instant t. Then the rate of decay is proportional to n. The rate of decay is given by dN by dt, where dN is the number of atoms disintegrating at time dt, then dN by dt is called rate of radioactive decay, that is directly proportional to n, where n is the number of atoms present in the sample at that instant of time, or dN by dt is equal to some constant into n. That constant is taken as lambda with negative sign. So dN by dt is equal to minus lambda n, where lambda is a constant is called decay constant or disintegration constant. The negative sign indicates that the number of nuclei decreases with time. So from this formula, dN by dt is equal to minus lambda n, and dN by dt is called activity. Solving above equation, we get the expression for number of nuclei remaining in the sample at any instant of time as n is equal to n naught e to the power of minus lambda t, where n is the number of nuclei remaining in the sample and n naught is the initial number of atoms, that is number of atoms at time t is equal to 0, and lambda is the decay constant, t is the time. Here lambda is the decay constant and its unit is per second, SI unit is per second or per day, and also you can measure in per year. N naught be the number of radioactive atoms present initially, that is at time t is equal to 0, n be the number of radioactive atoms present at any instant of time t. Next we have to know some important terms, that is radioactive half-life period of a radioactive nucleus. The half-life period is the time during which the number of radioactive atoms will be reduced to half the original number, is known as half-life of a radioactive element, or it is also defined as the half-life of a radioactive isotope is the time taken for which half of the nuclei to decay. In other words, the time taken for the activity to fall to half of its starting level. The half-life T of an isotope is the time in which one half of its unstable nuclei will decay. So the half-life is also defined as T of an isotope is the time in which one half of its unstable nuclei will decay. And here n is the number of atoms present at any instant of time, and n naught is the initial number of atoms at t is equal to 0. So n by n naught is equal to half. So that is equal to e to the power of minus lambda t from the given expression, and take the reciprocal of this. So here n by n naught substitute of. So half is equal to e to the power of minus lambda t, or 1 by 2 is equal to 1 by e to the power of lambda t of. Therefore e to the power of lambda t of is equal to 2. Taking natural log on both sides, natural logarithm and exponential will get cancel each other. So lambda t of is equal to ln 2 logarithm of 2, and take common logarithm by multiplying 2.303. So 2.303 into log of 2, that is 0.3010. After multiplication we get ln 2 as 0.693. So half-life period T of is equal to 0.693 by lambda. This is the expression for half-life. Next we will know about the mean time, represented by tau. The average life or mean life of a radioactive sample is the ratio of total lifetime of all number of atoms in the sample to the total number of atoms which will disintegrate anywhere between 0 and infinity. Therefore, mean life tau is equal to ratio of total lifetime of all atoms, or lifetime of all atoms over total number of atoms. So mean or average life is defined as ratio of total lifetime of all atoms present in the sample to the total number of atoms. Mathematically, it is given as tau is equal to T1 dN1, where T1 is the time or average time of the atom 1, and dN1 is disintegration of the number of atoms, like that, plus T2 dN2 plus etc. So divided by dN1 plus dN2 plus etc. is equal to sigma of T dN over dN. Mathematically, so the mean life or average life is given by this expression. The mean or average life of a radioactive element is thus not the same as its half-life. The mean life of a radioactive substance is also defined as the reciprocal of the decay constant, that is tau is equal to 1 by lambda. We can obtain the expression for mean life as tau is equal to 1 by lambda, that is reciprocal of the decay constant. And also we can obtain the relation between the half-life and mean life. We know that half-life is 0.693 by lambda, but 1 by lambda is equal to tau, that is mean life. Therefore T of is equal to 0.693 into tau, that is mean life. So half-life is equal to 0.693 times the mean life. This means half-life is less than the mean life or average life. Or average life or mean life is always greater than half-life. Next we will know about the term activity. The activity represented by A of a radioactive sample is the number of nuclei of the substance decaying per second. So the number of nuclei decaying per second is called activity. The rate of decay for radioactive substance is expressed in terms of the activity A, given as A is equal to dN by dt. If dN number of atoms in a substance disintegrate in a time dt, then activity is given by A is equal to dN by dt. This activity is measured in terms of becquerel. So becquerel is the SI unit of activity. Define 1 becquerel. So 1 becquerel is the activity equal to 1 disintegration per second. If any radioactive substance emits 1 nuclei per second, that is 1 disintegration per second, then its activity is called 1 becquerel. The other units are also used to measure the activity. They are curie, represented by Ci. 1 curie is defined as it is the activity of a radioactive material that decays at the rate of 3.7 into 10 power 10 disintegration per second. That is equal to 3.7 into 10 power 10 becquerel. Then the activity is called 1 curie. That means 1 curie is equal to 3.7 into 10 power 10 becquerel. The other unit is Rutherford, so represented by RD. 1 Rutherford is an activity equal to 10 power 6 disintegration per second. That is 1 Rutherford is equal to 10 power 6 becquerel. So SI unit is becquerel. 1 becquerel is 1 disintegration per second. The other units are curie and Rutherford. 1 curie is equal to 3.7 into 10 power 10 becquerel or 3.7 into 10 power 10 disintegration per second. The other one is Rutherford. 1 Rutherford is 10 power 6 disintegration per second, or 1 Rutherford is equal to 10 power 6 becquerel. So the same reasoning will apply to activity or to amount of material. In general, the following three equations can be applied to radioactivity. So nuclei remaining in the sample can be calculated as n is equal to n naught into 1 half to the power of n, or 1 by 2 to the power of n. Similarly, activity can be calculated as r is equal to r naught into 1 by 2 to the power of n, and mass remaining in the radioactive substance can also be calculated by this formula, m is equal to m naught into 1 by 2 to the power of n, and the number of half-lives can be calculated as n is equal to T over T off, where T is the time taken, lifetime period, and T off is the half-life period. N is the number of half-lives. Artificial radioactivity. So from this slide we are studying about the natural radioactivity. So what is artificial radioactivity? Artificial radioactivity or induced radioactivity is the phenomenon in which lighter elements can be made radioactive by bombarding them with high energy neutrons, alpha particles, protons, deuterons, etc. This phenomenon is called artificial radioactivity. That means radioactivity can be induced in lighter nuclei also by bombarding that stable nuclei with protons, neutrons, alpha particles, etc. They become unstable. To attain stable configuration, they emit alpha, beta and gamma rays. That phenomenon is called artificial radioactivity. I have used all these books as reference to prepare this video. Thank you for watching. Thank you once again.